Today, we want to get into more derivative shortcuts. This week is going to be about more derivative shortcuts. And we're going to start with our favorite one. Start with the one that we've been using this whole time, even though we didn't know it. That's called Palmolive style. No one knows what that reference is, and that's okay. I'm the oldest person in the room. Our first one is we're going to look at the chain rule, which is for finding the derivative of a composition of functions. Right now, all we have is nx to the n minus 1. We have to be able to write everything as powers of x. So right now, all we have our only shortcut so far is nx to the n minus 1. We have to be able to write things as powers of x. This is very limiting. So first, we're going to look at the chain rule. This is a rule for finding the derivative of a composition of functions. By composition, I mean one function has been plugged into another function. So one function, and then we do another function. That's a composition of functions. We do have notation for this. Although it's less common, you make a small circle. And so this would be the composition of functions f of g of x. First, you apply g to x, and then you apply f, the result. So this is our notation for f of g of x. So this is telling you to do two functions to x. First, you do g, then you do f. We don't see this very often at this point because we have a more useful way to write this. We say f, and usually it comes out right when we define what f of g of x is. F of g of x is f of g of x. So this is a composition of functions. First we do g, then we do f. So for example, if f of x is x squared and g of x is sine x. Then f of g of x, first we would do g of x, first we would do sine of x, and then we would square the result. So f of g of x, first we would do sine of x to the x, and then we would square the result. We have a different way of writing the square of the sine of x. We usually say sine squared x. So sine squared x is us trying to say the square of the sine of x. Hard times before we had this because we had to write the parentheses with the 2 on the outside all the time. And someone comes along and is like, I'm going to start writing this sine square x. And everybody's like, oh, yeah, that's good. Notice that this operation is not commutative. If I switch the order around, then I'm doing things in a different order. So if I write g of f of x, I would first do x squared. First, I would do f of x is x squared, and then I would do sine of x squared. I don't know why sine is being so standoff with the x squared. One of the main things that we want to recognize is that if we want to try to type sine of the square of the sine of x, we need these parentheses. If we just write sine x squared, this is how it should be read. So if I just write, let's note. If you just write sine of x squared, that's the second one. You definitely read this as sine of x squared. If you want the square of the sine and not the sine of the square, then you can either put parentheses around the whole thing, or if you're typing, if you want single line syntax for sine squared x, this makes it very clear that the exponent of 2, there's an exponent of 2, that's the to the 2, sine to the 2, that attaches the exponent to the sine. We don't need any more parentheses. This is clearly saying we're squaring the sine. If we don't like this, like if you look at this and you find this offensive aesthetically, that's okay. I agree. This looks offensive aesthetically, but I will accept it. If you want to put parentheses to make it look you have to use parentheses, and it seems like an excessive amount of parentheses. You'd have to say sine of x, close the sine, close the x, close the sine, and then square. If you just put sine, parentheses x, and then the exponent is getting applied to the x, not the sine of x. Any questions? So that's how, but if you just write sine x squared instead of sine squared x, it's going to be read as sine of x squared. So in single line syntax, this would be like sine x squared. That exponent applies to the x. Exponents only ever apply to what they're right next to. The exponent is right next to the x, not part of the sine. Any questions? This is important because we have to type some things sometime. How's everybody okay? Too fiddly for a Monday? Sorry, it's a math class. We're going to be pedantic up in here. All right. What we want to be able to do is take the derivative of a function that's a composition. We want to be able to take the derivative of a composition of functions. And for that, we need the chain rule. We need to be able to read functions as compositions. We need to be able to read an inside and an outside function. Here, I was giving you the two parts and asking you to put them together. We have to be able to look at a composition of functions and take it apart. One of the things that you're learning right now is not just mathematical concepts like what is the slope of the tangent line, how do we find that? How do we push the symbols around the page? But look at a bunch of symbols and read what it's telling us. Think about what's happened. So for example, let's suppose that I'm just going to use y to avoid this. 1, 2, 3, I need a 4. I'll use 4. We want to read this as a composition of functions. We know that if all we have is nx to the n minus 1, if we had to, we could multiply this out and write a bunch of powers of x. But then we look at this, this is an x squared to the 4th. This is going to be an 8th degree polynomial, and we do not want to write it out. There is maybe like 1 or 2 of you like, well, no, I totally want to multiply that out. I'm going to multiply it out right now. And it's just like you've written 4 copies of it, and you're starting to multiply. It's like all superfoil. That's the look of, I don't want to do that. So I know some of you are already working on it. Some of you are thinking, oh, I'll just use Wolfram Alpha to multiply this out. It's like, oh, dude, if you're going to use Wolfram Alpha to multiply this out, just use Wolfram Alpha to find the derivative. If you're going to throw technology at a problem, throw technology at a problem. You know what I mean? That's like the whole electric cars thing. It's like, oh, we don't need different cars. We need to get rid of the cars. That cars are the problem, not the motor part of the problem. If you're going to throw technology at it, fix the problem, not some piece of the problem. Do you know what I mean? But, you know, companies like, oh, but we need to sell something to everybody. Hey, set it up so everybody has to have one of these. You know what I mean? The words that I'm going to use are probably terrible, but these are the words that were inflicted upon me when I was learning calculus. I think about an inside function and an outside function. I hate it. I can't get rid of it. Every time I try to switch from inside to outside, it just gets wrecked. So what we want to do is identify an inside function, the one that that actually happens first, and then an outside function, the one that we do to the inside function. So we want to identify an inside the inside function is the one that would happen first in the order of operations. So in our description, f of g of x is the inside function. It's the one that goes first. And then we want to identify the outside function. This is the one that gets applied to the inside function. These are the words that I was programmed with as a youth. So these are the words that I'm going to use to program you. Because that is how you pass trauma along. So in this case, our inside function is the x squared part. That's, if we were going to evaluate this function, the first thing we would do is drop it into x squared plus 2x minus 3, except for the two of you that have multiplied this out already. Then you do you. The first thing that happens is we do x squared minus 2x minus 3, and then we take the result of that and put it in 5 something to the 4th. So our g of x, our inside function, so g of x in this case is the x squared plus 2x minus 3. Our outside function, which is f of x in this description, is 5 times some stuff to the 4th. I leave the space blank rather than writing 5x to the 4th. It's 5 stuff to the 4th. That helps remind me that there's more than just x. It's a reading exercise. We look at 5 times a bunch of stuff to the 4th. And I think, what would we do first? We would first do the x squared plus 2x minus 3. Then we would do 5, that thing to the 4th. Just reading the order of operations. The improved version of order operations where we're reading things, not just like spouting PEMDAS, because PEMDAS is trash. We want to be able to read inside, outside functions. So like up here, when we have sine squared x, we want to read that as the square of the sine of x. The first thing that happens is sine x. The second thing that happens is we square. When we read sine of x squared, we want to read the first thing that happens is x squared. The second thing that happens is sine. We want to read the order of operations, even when we have trig functions or polynomials as our whole thing. Let's talk about the chain rule. This is how to take the derivative of a composition of functions. So what we want is the derivative of some f of g of x and I want the derivative of this composition. I'm going to use prime notation for this. Make sure you get all the parentheses in play. Parentheses f, parentheses g, parentheses x, close, 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 prime. This is the derivative of f of g of x. Here are the words that I use for the chain rule. I say take the derivative of the outside with respect to the inside. The other way I say that is take the derivative of the outside, leaving the inside alone. So that looks like take the derivative of f with respect to g. The derivative of the outside, leaving the inside alone. The derivative of f with respect to g. Then multiply by the derivative of g with respect to x. We're just multiplying. That first factor is the derivative of f with respect to g. So we're going to read that as the derivative of f with respect to g. Another way I will say this, because it's a habit, is this is the derivative of the outside, leaving the inside alone. I don't like that phrasing, but I can't stop doing it. That's the first thing. Derivative of f with respect to g, the derivative of the outside, leaving the inside alone. With respect to g means we just leave g as it is. then multiply by the derivative of g, multiply by the derivative of the inside. Multiply by the derivative of g with respect to x. This is what the chain rule, how we'll write the chain rule, how we'll write and say the chain rule in Newton style notation. In Leibniz notation, we would say the derivative of f with respect to g. So that would be the change in f divided by the change in g. So df over dg. Take the derivative of f with respect to g. Then multiply by the derivative of g with respect to x. Take the derivative of the outside, leaving the inside alone. Multiply by the derivative of the inside. I wrote x. I spelled g wrong. Df dg times dg dx. Try to clean that up so it's not like d blob dx. So that's what the chain rule would look like in Leibniz notation. Thinking about it in terms of slope, delta y over delta x. If you're looking at this and saying, do the dg's cancel out? Kinda, yeah. Are we just doing unit conversions? Kind of, yeah. If you want to take miles per hour and write it as something else, you take your miles per hour, then you multiply by the rate of change of feet per mile, then you multiply by the rate of change of hours per second. There are probably better physics and chemistry examples, but I'm a math person. What do you expect? Let's look at this example. So for example, we've still got y is equal, it's jumped off. Oh, it's still on the screen. So if I want to find dy dx, I'm going to take the derivative of the outside with respect to the inside. What's the derivative of 5x to the fourth? So if f is 5 times something to the fourth power, what's f prime going to look like? What's the derivative of 5 stuff to the fourth? 5 times 4 stuff to the third, or 20 stuff to the third. Very technical terms, stuff. So the derivative of 5 to the fourth is 20 times that stuff to the third. So the derivative is going to be the derivative of the outside, leaving the inside as it is. And then we're going to multiply by the derivative of the inside. So g, the inside, is x squared plus 2x minus 3. So g prime will be 2x plus 2. Those first two factors make df dg. That second factor makes dg dx. How's everybody okay? Everybody got it? Incorrect. We've done one example. It is not possible that you got it. I have shot one free throw in my life. Like, that's one successful free throw. Does not mean that I got it. I just happened to be lucky one time. I think it's literally only one. Now that I've given out all the answers to the test on Thursday that I'm not going to be posting on Canvas, let's do some more examples of the chain rule. I'm just kidding, if you just came in. I only gave out half the answers. I'm just kidding. I gave out none of the answers. Even still, I don't know what. So all I've done here is I've changed the inside function. So this function reads 5 stuff to the 4. Stuff is 3x minus 2. It's a little simpler version of this. So we take the derivative of the outside, so dy dx, or y prime if we like, is the derivative of the outside, 20 times that stuff to the third. With the derivative of the outside with respect to the inside, so leaving the inside alone. And then we multiply by the derivative of the inside, which in this case is just 3. This one we would probably clean up because there's a 20 and a 3. We would want to clean those constants up. Sixty times 3x minus 2 to the third. Any questions? It's a reading exercise. We want to, what's going first? What goes next? Main thing I wanted to do here was, instead of writing dy dx, write y prime. One thing that we do want to point out is that we have been using the chain rule all along. It's just that the inside function is always just x, and the derivative of x is 1, and we don't say times 1. We've all been silently saying times 1, but we don't write times 1. You've all been saying times 1 when you do a derivative, right? Not writing it, but you've been thinking it, right? Right? Right. It's okay. I didn't tell you that you had to do that. So note. Sometimes the inside is just x. So the derivative of the inside is 1. So you have been, you just haven't been writing it. You haven't been thinking about it. Now you're going to be thinking about it. So for example, if our function y is equal to 5 times x to the 4th power, we'd say the derivative of the outside is 20 times x to the 3rd power, and the derivative of the inside is 1. So I guess I should put in a end loop. Stop when you get to a constant, because otherwise. This 5 times stuff to the 4th power, saying we're multiplying by 1, this is not far off of, let's say, 5 times 2x to the 4th power. In this case, y prime. Derivative of the outside is 20. Stuff to the 3rd, leaving the inside alone, times the derivative of the inside, which is 2. Which we would probably clean up as 40 times 2x to the 3rd, which is also a little bit messy. 2 to the 3rd is 8. 8 times 40 is 320. X to the 3rd. This is where we would have ended up if we looked at 5 times 2x, 5 times the 4th power of 2x and thought 2 to the 4th is 16. 16 times 5 is 80. It's good that both routes led to the same result. If 2 routes lead to different results, one of those results is wrong. Keep in mind that if one of your results is wrong, it's still possible that both of your results are wrong. So it's not like you have to say, one of these is correct. That's not the same as saying one of these is incorrect. Both of these incorrect includes one of these is incorrect. Does that make sense? All right. And if both are incorrect, don't just find the average. That's not how it works. Any questions, comments, snide remarks? All right, that's it for today. First thing is the chain rule. We're gonna need some more basic functions. So tomorrow we'll learn some more basic derivatives. That's it for today. I'll see y'all on tomorrow. Everybody have a good day and thanks for playing.